Identify the first mechanistic step in the reaction shown below. So in order to identify the mechanism, we really need to take a look and see what sort of reaction it is that we are dealing with. So we notice that we have an ester that we are starting with, and we are forming a different ester as a product. So this reaction is definitely a trans-esterification reaction. So that's a reaction where you take one ester and you replace the OR group to make a different ester. And we know that we can do this reaction under acidic conditions, or we can do it under basic conditions. So we want to look at what we are given here. So right away, you should notice this is the alkoxide, right? Whenever you have a sodium, that is a positively charged counterion. So that means that this structure is actually the alkoxide with the sodium counterion. So you see that alkoxide, the neutral alcohol, heat, these are basic conditions. And this is going to be important to thinking about the mechanism. That means that you are at a higher pH value. And if you're under basic conditions, strong acids cannot exist. So strong acids cannot exist. Right, so that means we don't have an acid catalyst protonating anything. So like right away I look at A and I see this protonated alcohol. That's a pretty strong acid. That does not exist in basic solution. So this acid cannot exist in basic solution. So this option A actually looks like the first step if you were to be doing this as an acid catalyzed process. If instead of using the alkoxide, you use the alcohol, heat, and acid catalyst, then this would be the first step. But it's definitely not in this case. And so we can't have a strong acid, so we're not going to be able to protonate the carbonyl. So the first thing that happens in this sort of mechanism is just that your nucleophile is going to attack the carbonyl carbon. And then all of your attacks on carbonyl carbons are all going to do the same thing. Your nucleophile attacks and you break the pi bond. So you always have that as a first step, and that's going to give you a tetrahedral intermediate. So there's where we've broken that pi bond. You still have the OCH3 attached, right? That hasn't come off yet in this first step. And you've added this new bond to your ethoxy group, essentially. So that would be the first tetrahedral intermediate that you would form. Tetrahedral intermediate. Okay, and so we're looking for just the first step. So we can look at this step here, these arrows, and try to find that, and that is option C. But if we wanted to, we could actually finish this reaction. In basic conditions, these mechanisms are pretty quick. So after you get to this tetrahedral intermediate, your electrons are going to come back down and you're going to kick off a leaving group. And so notice that in terms of leaving group ability, these are pretty much identical, right? You're comparing methoxide to ethoxide. They're pretty much the same in terms of their basicity. So the way that we push this reaction forward is by kind of having an excess of this around, having an excess of its conjugate acid as the solvent to push this equilibrium forward that way. So we're going to draw the arrows that lead us towards product. So you kick off that OCH3 minus. So now you have that ester you're looking for. You've also formed methoxide. And if you have ethoxide as your solvent, you can imagine that the methoxide could pick up a proton from that ethanol, because we're going to try to form this methanol as well. So this can pick up a proton from that ethanol, and so that's going to give you the methanol. It's also going to regenerate another equivalent of ethoxide. So we're keeping a good concentration of this so we can keep pushing this equilibrium towards the ester that we want.